Okay, this video is going to look at radioactivity. And you probably know there are three types of radioactive decay. You have alpha decay, and this is when the nucleus gives gives off two protons and two neutrons, basically a nucleus of helium. You can also have beta decay, where you give off an electron. But the important thing about this electron is it comes from the nucleus, and it is formed when a proton decays into an electron. Sorry, when a neutron decays into an electron and a proton. So when beta decay occurs, atomic number increases. And then you have gamma radiation, which is simply shortwave uh, electromagnetic radiation. And gamma decay always accompanies alpha decay and beta decay, because these decays occur in order for the nucleus to lose energy, and the energy is given out in terms of gamma radiation. So what we're going to do is explain the phenomenon of radioactivity. I'm going to write equations representing nuclear reactions involving alpha, beta, and gamma emissions, and mention the neutron to proton ratio. For example, representing alpha decay, where we have 22388 radon going to 21986 sorry, Ra is radium going to 21986 radon plus 42He, or alpha particle. And properties of the particles are not required of positron. We're going to mention positrons, but we're not really going to look at them in any detail. I'm going to cite uses of radioisotopes and calculate the relative atomic mass of an element given isotopic masses and abundances. I think we've covered that anyway in a previous class. So why do atoms emit radiation? So the nucleus is unstable due in part to the ratio of protons to neutrons. We'll look more about that later on. So if you have an unstable entropy ratio, that is neutrons to protons, and the nucleus will decompose and give off energy. So as well as giving off an alpha particle or a beta particle, it will give off gamma radiation. And atoms emit radiation and lose energy. And by losing energy, they become more stable. And they can have artificial radioactivity. This is the radioactivity of a nuclide produced bombarding stable isotopes with small particles like neutrons or alpha particles. And it is known as artificial radioactivity or induced radioactivity. And the Joliet Curies received the Nobel Prize in Chemistry in 1935 for the discovery or artificial or induced radioactivity. We're not going to say any more about that. So this part's important. You have alpha decay. It gives an example of alpha decay here. And notice in alpha decay, well, in alpha decay, the atomic mass will decrease by 4, and the atomic number will decrease by 2. In beta decay, the atomic mass is unchanged, but the proton number will increase by 1. In gamma decay, nothing happens, in terms of atomic mass or atomic number. This thing accompanies alpha decay and beta decay, and really occurs afterwards. So gamma decay is just the means by which nuclei give off energy. You have positron emission, where you have a thing called a positron, which is really a positively charged electron. And you also have an electron capture, where an electron is captured by the nucleus and a proton changes into a neutron. But positron emission and electron capture, we're not going to say anything more about these. So examples of equations. Note in the first one you have iodine, and it's giving off a beta particle. So the atomic mass, the atomic number increases, but the atomic mass stays the same. Then you have radon giving off alpha particle. So its atomic number decreases by 2, and its atomic mass decreases by 4. So the sum on this side of the arrow, 86, is equal to this side, and 216 is equal to 4 plus 212. And you can identify the element by looking at a periodic table. So 243 Einsteinium gives off a beta particle, so its atomic number will decrease by 2, and its atomic mass will decrease by 4. And you have deuterium giving off a beta particle, so its atomic number will increase by 1, but its mass number stays the same. So we can try some for ourselves. For aluminium, there's an error here. Aluminium should be 13. So it's in fact gaining a helium nucleus. So its atomic number is changing to 15, and that's phosphorus. At the same time, the mass number is 30, but on this side you have 31. So you need to it's giving off a neutron as well, and you have one of these. For the next one, you have 6329 is copper. It's gaining a hydrogen atom. So its atomic number is changing to 30, which is zinc. 63 plus 2 is 65, but this is still 63. So that's why you have 2 neutrons being given out, and therefore you need a 1 of this. This one, you have 65 going to 65, 30 going to 29. So you're going to have 0. This is in fact giving off a positron. So this is 0 plus 1 E. And then you have 9 for beryllium. 9 plus 4 is 13. You have 12 here. So you have a 1, 0, N plus 4 plus 2 is 6. And you have 6. So you have 0 and 1 N. See if those are notice aluminum, it's 13, not 12. And this one is a beta positron. We're not really going to go into any more detail of those. And there's others which we can do for yourself. And the answer is given. So can look at that. So in a graph of the Newton number against proton number, the graph is plotted for all known nuclides. This is P equals N, a straight line. For low atomic numbers, a stable entropy ratio is almost equal to 1. But as a proton number increases, entropy ratio also increases. You need more neutrons present in the nucleus to keep the nucleus stable. And that's because protons, being positively charged, repel each other, and the neutrons minimize this repulsion. And this graph, this illustration, indicates what type of emission will occur. So if the entropy ratio is larger than 1, you expect beta emission to occur. If entropy ratio equals 1, you have no radiation. And if the entropy ratio is lower than 1, then you have positron emission or alpha emission. And the one that we're going to be interested in is alpha emission only. So what type of decay will carbon-14 undergo? And we know the stable entropy ratio is 1. Carbon has an atomic number 6 and therefore has 6 protons. And the number of neutrons is 14 minus 6, which becomes 8. And therefore the entropy ratio is 1.33. Decay must bring it close to 1. So if alpha decay occurs, the entropy ratio goes to 1.5. So the MP ratio is further from the required value, so it will not occur. And therefore we know that beta decay occurs. And that is why if entropy ratio is larger than 1, beta decay must occur in order to bring the entropy ratio closer to 1. And if the entropy ratio is smaller than 1, alpha decay will occur to bring the entropy ratio closer to 1. So what are the uses of radioactivity? Well, it can be used to see if organs are working properly. For example, the thyroid gland. So you can use radioactive iodine, and we can see if the thyroid gland is working correctly. And also, you can use radioactivity to kill cancer cells. It can also be used to sterilize food and medical equipment. It can be used to control thickness in industry. It can be used to find leaks in pipes. There are other things such as carbon dating or radioisotope dating. So iodine-131 is used in testing for thyroid gland. So you need to remember that part. Iodine-131 is used for testing for functions of the thyroid gland. And it mentions that radioactive iodine uptake the patient swallows a liquid or capsule containing radioactive iodine. A probe is then placed over the thyroid gland along the outside of the neck and checks the function of the thyroid's ability to absorb and retain iodine. An ultrasound access the size of the thyroid gland. And you can use cobalt-60 for food sterilization because it's a good emitter of gamma rays. and another is cesium-137. So for cobalt-60, it can be used for the inhibition of sprouting of potatoes, onions, garlic, ginger, and yam. It can be used for insect parasite and disinfectant for cereals, fresh fruit, and dried fruit. And it can delay ripening in fresh fruit and vegetables. A medium dose can extend the shelf life of fish, strawberries, mushrooms, and halt spoilage that kill pathogens in seafood, poultry, and meat. And of course, when you treat these foods with radioactive isotopes, all you're using is the gamma radiation. So the food doesn't really come into contact with the radioactive isotope itself. And therefore the gamma radiation is long gone when you consume it, and therefore it's not harmful. They have high doses for industrial sterilization of meat, poultry, seafood, prepared foods, etc., and decontamination of spices. So we can use cobalt-60 for food sterilization, or we can also use cesium-137. For these, all we're interested in is the gamma radiation, and therefore, provided the source is a good gamma emitter, that's all we're interested in here. So, medical applications of radioisotopes and in cancer treatment. In external beam radiation therapy, gamma radiation generated from cobalt-60 is aimed at a tumor, destroying the tissue. So to kill all both healthy cells and cancer cells. But the intention is to kill the cancer cells. In brachytherapy, small titanium seeds containing radioisotopes are implanted in the tumor. And these things will emit gamma radiation and kill the tumor. So in brachytherapy, small titanium seeds of palladium-103 or iodine-125 are implanted in the tumor site. Other applications. Cobalt-60 is used to prevent cancer. Iodine-131 is to locate brain tumors, monitor cardiac, liver, and thyroid activity. Carbon-14 is used to study metabolism changes for patients with diabetes, gout, and anemia. Carbon-11 can be tagged onto glucose to monitor organs during a PET scan. Sodium-24 is used in blood circulation. Thallium-201 to determine damage in heart tissue. And technetium-99 to locate brain tumors and damaged heart cells. Moving on. Americium-241 for uniform thickness when rolling steel and paper, and for the determination of the location of oil wells. Sodium-24 for oil well studies. Iridium-192 to test integrity of boilers and aircraft parts. Uranium-235 for nuclear power plant and naval propulsion systems. And Californium-252 to determine the moisture content of soil, and it's important for road construction and building industries. There are further things like carbon-14, which will decompose into nitrogen-13. These are half-lives of different isotopes. These ones are probably used for radioisotope dating. Things with a long half-lives are useful for radioisotope dating. So notice, for example, carbon-14 has a useful range of 100 to 30,000 years, So we don't really use carbon-14 for dating fossils, which are millions of years old. We can use potassium-40 for that, or rubidium-87, or uranium-238. Well, that only goes to 10 million. Well, you probably know that the age of the Earth, or this age of the solar system, is about 4.6 billion. So uranium-235 can be used to determine the age of the solar system. And you can do the same thing for potassium-40. The next thing shows how to work out the mass of isotope. I think we've done this before. You simply find the abundance of each, multiply by the percentage by the atomic mass, and then divide by 100. So this calculation is given here. It's important you can do these calculations because they're fairly straightforward, and they can be worked out using a mass spectrometer. And a mass spectrometer will ionize some chlorine molecules to form chlorine ions, and some of them will exist as atoms, and some will exist as ionized molecules. And since chlorine has two isotopes, you'll find 4 peaks, 2 for the atoms, and chlorine-35 is much higher than chlorine-37. Chlorine-35 is more or less 75, and chlorine-37 is more or less 25. So that's why this peak is much higher. For these peaks, two chlorine-35s is the most likely, because chlorine-35 is more common than chlorine-37. And then chlorine-35 and chlorine-37 will be higher than the chlorine-37 or chlorine-37 peak. So that's why we have those 5 different peaks. This graph is important because it's often given in multiple choice questions. So nuclear energy then. There are 2 types. Is nuclear fission. When you hit a nucleus of an atom of a neutron, and it breaks up into smaller nuclei. It's a bit like playing pool, and you hit a ball with a cue ball, and all the balls scatter. Where you can have fusion, where you have 2 nuclei, and they come together to form a larger nucleus. For example, we encounter that in the sun, where you have hydrogen atoms coming together to form helium. That's an example of nuclear fusion. And nuclear fusion also gives off a lot of heat. And it can be used in nuclear reactors, where we have fuel elements which are giving off energy. We've got to prevent this reaction from giving off too much heat. So we have control rods which can come in and out. When they come in, they absorb all the neutrons given off by the different fuel elements. And this will prevent chain reactions from occurring. And when you move them up, then neutrons from different fuel rods can go into the next fuel rod and then generate more energy by forcing the decomposition of other nuclei. And the heat is used to convert water into steam. And the steam is then under high pressure and is used to turn a turbine. And nuclear energy has pros and cons. Pros, it's inexpensive. Con, it has an environmental impact. Another pro is its low greenhouse gas emission. But another con is nuclear accident. Another pro is power output is maximum. However, they're expensive and long time to build. It's a reliable source of energy, but there's a security threat. If you've been following the Russia-Ukraine war, there's been a problem at a power station because people have been fighting close to it, and there's a danger of an accident which would affect most of Europe. Another pro is a positive economic output, but a con, nuclear energy is not renewable, so eventually we'll run out of nuclear fuel. I also added nuclear energy has high startup costs. I don't think this was mentioned. Well, it did say expensive. So it's probably mentioned actually. And then there's a danger of nuclear weapons. And I gave a YouTube documentary for you to watch concerning that. And that basically completes this discussion.